Good evening to everyone. So I'm Engineer Mustali Shahid, Chairman of IT and Computer Engineering Section Committee. So thank you for being here with us today. On behalf of IT and Computer Engineering Section Committee, I'm pleased to welcome all of you today our session on high precision remote geotechnical and structural sensor data collection for critical infrastructure project. So without taking your time, I would like to introduce our guest lecturer today for the session. So Dr. Nimanta Baranasuriya is the co-founder and CEO of Axio, a deep tech company that is building state-of-the-art real-time wireless monitoring solution for industrial monitoring applications. Nimanta heads the overall business operation of Axio. So Axio flagship product, Axio Beam, is used in construction, mining, rail, and infrastructure industries to automate monitoring of geotechnical and structural sensors. Axio is headquartered in Singapore with a subsidiary office in Canada. Also, solutions have been deployed in over 25 countries to monitor critical projects to increase safety and manage risk. Before starting Axio, Nimanta obtained his PhD from the National University of Singapore, specializing in wireless networks. Some of his PhD research has been awarded to patent and has also been used to improve the quality of Skype calls. Nimanta specialized in computer science and engineering at the University of Marathon, Sri Lanka, where he was the gold medalist of his batch. He was also the winner of the Most Outstanding Graduate Award, which is the highest accolade awarded to an undergraduate at the University of Marathon. So as a young entrepreneur, Nimanta is a strong advocate for entrepreneurship and believes in running startup ecosystem to make the world a better place. In his spare time, he actively participates in sharing session and through leadership discussion to share his knowledge and expertise with other founders. So please drop your questions in the chat box and will be answered as soon as possible or at the end of the lecture. Once again, thank you very much and let's start the session. Dr. Nimanta, over to you.
Thank you, Mr. Very nice to be here. Let me share my screen. And yes, I hope you can see the slides.
Yes, Dr. Nimanta. Yes, we can see you.
Perfect. Yeah, so thank you everyone for being here today. It's a pleasure to be here to talk about what we do at Axio, and which is helping construction, mining, rail, and other infrastructure industries monitor various geotechnical and structural sensors by using wireless technologies to achieve cost savings, higher productivity, and higher precision as well. So before I get into the topic, I would just like to quickly introduce myself and the company, and then we'll go more deeper into this topic. So as I was introduced earlier, I'm the co-founder and CEO of Axio. Started Axio about 5 years ago after I finished my PhD studies at the National Institute of Singapore. And at that time, I wanted to do something industrial with the research expertise that I had gathered in wireless networks. My father is a civil engineer. He might be on the call today as well. So I was chatting with him one day about like using wireless technologies in the construction space. And he introduced me to one of his ex-colleagues who was at that point based in Singapore. So I called this engineer and I asked him like, what kind of problems do you face in work? And he told me that he works for a tunneling contractor. And while tunneling, they have to monitor various sensors, like thousands of sensors that can measure the load of the tunnel walls and other parameters. And because those sensors were monitored using very traditional practices, we'll talk about that later, like they were having problems in collecting the data to carry out their work in a productive way, in an efficient way. So that got me thinking, and we realized that there's a way that wireless technologies could be used in the construction space to automate various, to automate monitoring of various sensors, and that led to the starting of Axio. So before my coming back to my profile, before starting my PhD, again, I did my undergraduate studies in Sri Lanka at the University of Moratuwa, where I specialized in computer science and engineering, and then, of course, moved to Singapore for my PhD work, and then started Axio. So I'm pretty passionate about taking new technologies into the industrial space where like technology is lagging behind, unfortunately. So these industries like construction, mining, these are very important industries. They are like the lifeblood and they contribute to the economies of almost every single country. But unfortunately, as they are lagging behind in technology. So I take pride in helping these industries innovate and adopt new technologies based on the research and industrial expertise that I have. So that's about me. Talking about Axio, as I said, we build wireless monitoring systems for construction and mining, like kind of heavy industries. The name originates from Harry Potter. So if you're a fan of the Harry Potter movies or the books, you might recall that there's a spell called Accio that brings things far away from you to your hands. It's a summoning spell, and that's what we do in these industrial spaces. There's a lot of sensors that are deployed, and we help with our wireless technologies to bring that geotechnical and structural sensor data to your fingertips for real-time decision making. So we started Axio in Singapore in 2016. So we are a little bit more than 5 years old right now. And we have an office in Canada as well that is covering the North and South American markets for us. So we have our solutions have been deployed in over 30 countries across 6 continents, or in every case, they're helping these contractors monitor various critical infrastructure development projects. So this is a quick map to show where our clients or our devices have been used in various infrastructure projects. So as you can see, it's all over the world. So we support all these projects through our offices in Singapore, where we do the R&D and support work, and also our sales office in Calgary, Canada, that houses our sales and support engineers as well. So that's a quick introduction to myself and Axio. And right now, I would like to talk about how geotechnical and structural monitoring can be done using wireless remote technologies. So I'm dividing the discussion into 3 parts. Sorry, 1 second. Yep, this is an overview of the talk today. So first, we'll quickly overview the geotechnical and structural monitoring practices, like why it's important to do monitoring in infrastructure projects and how it is being done currently. And in this section, I'll also try to introduce wireless monitoring and talk about why wireless monitoring is better suited for monitoring infrastructure projects. Secondly, we'll take an overview. We'll do an overview of the currently available wireless monitoring technologies in the market. The technologies, basically, I'm not going to talk about brands or anything like that, like just the technologies, and we compare them and see the pros and cons of each. And finally, we'll move into wireless monitoring in critical infrastructure projects to show how geotechnical and structural sensors can be monitored wirelessly. And I'll talk about some case studies as well, where our solutions have been used to give you an idea of how this works in real life. So without further ado, let's get started and go into the first part, where we'll go through the current geotechnical and structural monitoring practices and discuss some of the problems that are associated with them. So geotechnical monitoring, just to introduce this area to people who might not be familiar with it, it's all about monitoring the earth and the structures in any infrastructure development project to ensure that the actual construction work follows the specs and the design work that have been carried out by the architects and other consultants of the project. So let's take this bridge as an example that's on the screen. So while this bridge was designed, the architects and the designers might have designed these columns to carry a certain amount of load. But while constructing, how do you ensure that these columns are carrying that exact amount of load? Like maybe the contractor did something wrong, and now the load that is being borne by one column member might be higher than the design limit. So in that case, it's a very dangerous situation because that column might develop cracks and collapse one day. And also while building, like let's say one of these columns start tilting because the soil is not very solid or something like that, which causes these columns to move. So if you are not monitoring the tilt of these columns, again, problems might occur and things might end up in a disaster. So this is why geotechnical monitoring is important. It helps engineers gather lots of data from the actual construction project and compare those data points with the design of the project and see whether something is deviating from the norm. So if something is deviating, they can take early action and prevent a very costly accident from happening. And if an accident were to happen, the consequences can be devastating, like people might even lose their lives. And also there might be monetary losses and delays of the project as well. So this is why geotechnical monitoring is very important. So people have been doing geotechnical monitoring for the longest time. I mean, this is not a new area. And there are so many sensors that help engineers and consultants get various data points from all their infrastructure development projects. So some simple examples include tilt sensors. You can place tilt sensors on any wall or any column that you want to monitor, and then check whether it's still straight or whether it starts tilting over time. And there are things like crack sensors. So if there's a crack on a certain wall, again, a crack sensor can be put against it to monitor whether the crack is expanding over time. Right? If the crack is expanding, it can be a dangerous sign. There are other sensors like soil water pressure sensors, like piezometers, that can be embedded in soil to monitor the soil water pressure. And those are very important in excavation projects where the water body of the soil is disturbed. And there are things like strain gauges or load cells that can monitor the load that is being carried by a beam or even a column. And there are like other complicated sensors like deformation sensors that which can go into the soil, like hundreds of meters into the soil, to monitor how the different layers of the earth are deforming because of excavation work or any other soil movements, right? So the sensor space is like quite diverse, and there are so many sensors in the market already that allows engineers and contractors and consultants monitor any parameter of their choice in their critical infrastructure development projects. But what's problematic is that these sensors are currently monitored using very legacy solutions. Meaning, like let's say you need to monitor a set of tilt sensors, piezometers, like even crack sensors in a project. So there are two main solutions that companies leverage for this monitoring purpose. One is workers. So they send workers with these handheld sensor readers to visit every single sensor in the site and take readings using this handheld sensor reader. So this process is very costly because it involves a lot of workers going around in the site monitoring sensors. And also it actually imposes a safety risk because when there are more workers in the site taking all the sensor readings, they can be prone to accidents in the site. And secondly, the accuracy of these readings can be low as well because the worker has to manually connect this reader to, like say, for example, the tilt sensor to take a tilt reading for the day. And while doing that, might be tired or like might not connect the sensor properly. And in that process might take incorrect readings from the sensors. And lastly, if you're using workers, it's very difficult to monitor sensors frequently. So at most, a sensor can be monitored once a day, which is problematic for certain projects like excavation projects where the earth and the structures might move very rapidly in a matter of like 24 hours. So those are the problems associated with using workers or manpower to monitor geotechnical and structural sensors. On the other hand, companies use cables. So when you're using cables, a cable has to be connected to every single sensor, and then these cables run through the entire construction site to a central computer called a data logger. So in this process, companies can lay like anywhere between 40 to 50 kilometers of cables. Like we've seen projects where there have been like over 50 kilometers of cables also that connect various geotechnical and structural sensors to a central computer. So this process is quite time consuming because they have to plan out the cable routes and connect all these cables to a computer, because you can just run cables through a construction site, they can get damaged. And cabling, of course, is very expensive. As I said, like there have been projects where there have been more than 50 kilometers of cables. And therefore, like they have to spend quite a lot of money on deploying cable networks. And also, because they are prone to damages, if a cable gets cut, the contractors don't have the data to take their decisions. So these are some pictures that were taken from an actual construction site that we've been to, where the contractor had laid like a huge cable mess to monitor all those sensors that they wanted to monitor in that construction site. And in a lot of countries, the process of monitoring geotechnical and structural sensors is regulated. Um, in Singapore, for example, if a certain sensor does not report data for a few hours, the contractors have to stop work, because without that sensor data, they're operating blind. Like, for example, let's say you're monitoring a tail sensor and the tail sensor's wire is now cut. So you don't know whether that column that you're monitoring is whether upright or whether it has started tilting or whether it has like collapsed completely. So that's why this process is important. It directly impacts the safety and the risk management of the project. And therefore, cables and manual monitoring solutions are pretty expensive to deploy. They produce erroneous data and also quite inefficient. So these are the problems. Yeah. So as a quick summary, so geotechnical structure and structural monitoring is important. There are various sensors that can be used to monitor various parameters in these projects. And currently they are used, they're monitored using workers and cable-based solutions, which have lots of associated problems. So when monitoring is not carried out properly, the consequences, the very serious consequences, or the final consequences are collapses or accidents. So the picture on the left is Singapore's biggest construction accident in its history. It happened in 2004 while a contractor was building an underground train system. So if you've been to Singapore, Singapore's train system is called the MRT system. And this happened while they were building the yellow line or the circle line MRT. So they were excavating the ground to lay the tunneling structure, and near this highway, the tunnel just caved in, and it led to like a huge collapse of a very long tunnel segment, and about 4 workers died that day as well. And yeah, after this, all the authorities in Singapore stepped up and increased the monitoring practices. So the investigations showed that the tunnel collapsed because it was not monitored properly. So since then, again, the regulations have been made really stringent, and now any excavation project, any major infrastructure projects are very heavily monitored using geotechnical and structural sensors. The one on the right is one of the biggest mining disasters in the world. It happened in Brazil about 3 years ago. In mines, there's a structure called a tailings dam, which stops, like when you mine the earth looking for precious metals and all, there's a lot of waste elements like mud, slurry that is being dug out from the mine. And this waste elements are stored inside a pond called a tailings pond, and then a dam is built around it to ensure that the mud and slurry do not like go out into the villages or the civilization surrounding the mine. But in Brazil, one day, like about 3 years ago, the dam that was holding all that mud and slurry collapsed, and it created a huge flood of mud, which wiped out a village that was right next to the mine, and it like killed about 200 people in Brazil, unfortunately. So these are, again, two examples of very severe collapses or accidents that have happened due to poor monitoring practices in construction and the mining industries. So moving forward, like so we discussed like the problems associated with legacy monitoring practices. So if monitoring is to be done in a real-time nature using remote monitoring technologies, there are many advantages that can be achieved. So one is workforce safety, because you're not sending in workers anymore to the site to take manual readings. You don't need to expose workers unnecessarily into hazardous environments, and therefore the safety of the entire project goes up. Secondly, most importantly, you can implement better risk management processes, because now you have a very seamless way of getting all the sensor data gathered from the entire project. You have the data at your in your fingertips to take real-time decisions. And so if something is, again, to keep things simple, let's say you're monitoring a tilt sensor, so you'll be like getting tilt data, let's say once an hour. So once an hour, you know whether the column that you're monitoring is upright or whether it is starting to tilt. And so before it like tilts a lot and collapses, you can take quick actions to investigate why the column is not tilting and take appropriate risk management solutions to ensure that the safety and the integrity of the project is not compromised. Thirdly, remote monitoring can help reduce costs, because now, again, you are dependent on less workers and less amounts of cables. The solutions, the wireless solutions that are available in the market now can help dramatically reduce costs of monitoring geotechnical and structural sensors. The fourth benefit is increased efficiency, again, because now you have seamless amounts of data coming in. You can take quick decisions, and the entire process of constructing the infrastructure project becomes quite efficient. And finally, the data is secure, and everything is integrated into one system, so which will help stakeholders like consultants, engineers, and everyone involved in the project understand what's happening in the project and take quick decisions as well. So these are the benefits of doing remote wireless monitoring. And just to show you like how this works, again, this is just an illustration. So I'm using a construction site in the background, which I've grayed out, to show how wireless monitoring would work as opposed to using workers and cables to monitor various geotechnical and structural sensors. So let's say there are sensors that are deployed all over the site. So let's take a tilt sensor again as an example. So let's say there's a tilt sensor that is monitoring a certain column or a wall in this part of the project. So this sensor would, and there would be similar sensors like piezometers, crack meters, deformation sensors, like all kinds of geotechnical and structural sensors, right, could be deployed in the site. So these sensors would be connected to a wireless transmitter called a node. So the sensor would have a small cable segment coming out of it. So it would be connected to, again, a wireless transmitter called a node. And so all the sensors, likewise, in the entire project would be connected to nodes in a similar fashion. Now, what happens is there are transmitters that are connected to the nodes. So there should be a receiver, and we call this receiver a gateway. So the gateway's job is to collect all the sensor data from all these various geotechnical and structural sensors, and then upload that data to a central software system or a server where the stakeholders can log in and see that data to take real-time decisions. So now, how is this different from the previous solutions? Well, if you're using manpower, you have to send a worker to every single one of these sensors to monitor them manually using handheld sensor readers, like what we discussed earlier. And if you're using cables, you have to run a cable from each and every one of these sensors to a central computer called a data logger. So instead of doing that, what you do is you connect a wireless transmitter instead, a battery. So these are battery operated, and therefore they can be placed anywhere where the sensor is. And that eliminates the workers, because now the wireless transmitters are transmitting, they're taking sensor readings and transmitting it wirelessly to the gateway. And the gateway then uploads that data to a central software system. So this is how the whole work site or the infrastructure project can be automated by using wireless technologies to monitor sensors in a more productive and efficient way. So when using these kind of solutions, the entire monitoring process becomes cost effective, because again, you're not using workers and costly cables anymore. The data is more accurate because there's no workers in the loop. It's an entirely automated system. The productivity is very high because you can monitor sensors very frequently. Like we've been we've had experiences in projects where our sensors were mounted every 5 minutes because there's a lot of movement in those projects. So when you have that amount of data coming in, you can take very quick decisions, which will increase the productivity of the construction work. And finally, and most importantly, the safety of the project goes up dramatically as well, because you are using less workers, and also this data that you gather helps you to keep the infrastructure development project safe. So that's part one, where we evaluated or looked at geotechnical and structural sensor monitoring process and the legacy solutions that have been used and the problems associated with them. And we also then looked at how wireless technologies can help automate the same monitoring process of existing geotechnical and structural sensors to do monitoring in a cost-effective and a more productive way. So in this section, what we'll do is we'll look at different wireless technologies that are available in the industry and see what the pros and cons are of each of those technologies. So if you look at the wireless monitoring space for geotechnical and structural sensor monitoring processes, there are two major technologies called star networks and mesh networks. So in star and mesh networks, again, the concept is quite similar as we discussed before. There would be a bunch of sensors, geotechnical and structural sensors that need to be monitored. And each of these sensors would be connected to a wireless transmitter, which we call the node. And the nodes have to take sensor readings periodically and transmit that sensor data to the central receiver, which we call the gateway. And the gateway then collects all the sensor data periodically and pushes that sensor data to a server where the data can be visualized and analyzed by engineers and other stakeholders. So in mesh networks also, it's exactly the same setup. You have sensors, you have nodes, you have a gateway, and you have the server. But what's different is the way that these networks operate. So in star networks, what happens is each node or each transmitter has to transmit its sensor data wirelessly directly to the gateway. Whereas in mesh networks, these nodes can talk to one another. Like they can still talk to the gateway, but apart from that, the nodes can talk to one another as well using their wireless radios. So how is this important in infrastructure projects? Well, in infrastructure projects in critical like industries like construction and mining, these are not very pristine environments. There's a lot of movements, there's a lot of machinery involved. There can be obstacles that can occur in the networks. Like for example, let's say there's a big building that's blocking the wireless signal from this node to the gateway. So in that case, because the wireless signals have difficulties penetrating obstacles, that link might drop, and now you're not getting any data from this sensor. So let's say this is a tilt sensor and that was affixed to a column. Now, because this node is not able to send its data wirelessly to the gateway, as the user, like as an engineer, let's say you're the engineer who's monitoring this project, now you don't see any data from this tilt sensor. So that becomes a problem because you don't know whether that column is still upright or whether it has started tilting. But in mesh networks, let's say the same building is there, and like what we discussed earlier, that link might disappear because there's an obstruction. But now the good news is you're still getting the sensor data through a different link or different path in the network. So that's the advantage of mesh networks. It gives each transmitter multiple ways of reaching the gateway. So if direct paths are linked, it will find a different path in the network. So they always choose the best path at any given time to reach the gateway. So mesh networks typically, therefore, gives a lot more reliability in monitoring various geotechnical and structural sensors in these kinds of infrastructure development projects. So looking at these spaces, so in star networks, the most commonly used technology that you might like if you study this space that you'll see is LoRa. In mesh networks, there are two major technologies that industrial products use. So these are actually radio wireless communication standards. So LoRa is one standard, Zigbee is another one of them, and Wi-SUN is another protocol. So in LoRa, the radios use the ISM spectrum, so the sub-gigahertz spectrum, which is unlicensed in almost every country. There's like a portion of this spectrum that can be freely used without a license, and that is the case in a lot of countries around the world. And also, these LoRa radios offer a very long communication range, like about 15 kilometers in line of sight environments. But when there are obstructions, of course, the range would drop a lot. In Zigbee networks, Zigbee networks use the 2.4 gigahertz spectrum, so the same spectrum that Wi-Fi and Bluetooth use, which, as you know, have a very short communication range. So they're not very suitable for industrial monitoring projects because there's a lot of obstructions and a lot of like movement in these kind of like critical projects, which practically makes Zigbee networks very hard to deploy. So the sort of hybrid between LoRa and Zigbee is actually Wi-SUN, which what we use in Nexio as well. So in Wi-SUN standard, we still use the ISM spectrum, so which is in the sub-gigahertz spectrum. That's like what we discussed earlier. Apart from that, it gives a very long communication range as well. So Wi-SUN can be seen as a best of both worlds. So you get a long communication link, and on top of that long communication link, you can form a mesh network. So we'll show how this works in real life. But when you have a long range mesh network, any infrastructure development project can be easily monitored. I'll show you an example to illustrate how that works in a little bit. So talking about the pros and cons of these two networking systems. So star networks are very simple to deploy. They are very simple to build as well. Because the complexity of communication is very simple. So there are LoRa chips that you can buy off the shelf, and you can just create a very simple LoRa-based communication system, which would actually work in very simple projects, or when there are not many obstructions around. Also, the power consumption is quite low because each transmitter has to just wake up, take a sensor reading and transmit it to the gateway and then go back to sleep. So let's say every hour there's a sensor reading to be taken. So the nodes will only wake up every hour, take a reading, transmit and sleep. So therefore, the battery lifetime of star networks would be quite high. But in terms of problems, they're practical only for small projects. So if you have very large projects or like a lot of obstructions and interference, these networks have difficulties in providing reliable communication. And also in underground environments like tunnels and like underground mines, star networks have very big difficulties in operating because, again, the obstructions don't allow them to communicate the data into like out of the tunnel. So in mesh networks, the advantages are they're massively scalable, so you can cover large projects and like even small projects and large projects, and even underground environments very easily. And also they're quite reliable, as we discussed earlier, like because each transmitter has more than one path to use for communication. If one path gets blocked, they can choose a different path. So the reliability of mesh networks are very high. In terms of negatives, mesh networks are a bit complicated to understand and deploy properly because it's not as simple as a star system. So you need to understand how the project is laid out, and then if you lay the network accordingly, the reliability can be very high. And compared to star networks, mesh networks draw more power from batteries. Therefore, the the battery lifetime of mesh-based systems is relatively lower than star networks. So that's a quick summary, but to show you using an illustration as to why star networks are like less practical in these kind of big infrastructure development projects. I'm going to use this satellite view of a project that we completed in Singapore last year. So this project is now complete. This was the construction area for a new underground MRT station or a train station in Singapore. So if you've been to Singapore, this is near the Orchard Road area. So as you can see, there are lots of high rises all around the construction site, and people were actually living in these buildings already. So when the contractor started to excavate the ground, the earth to build the train tunnel as well as the underground train station, they had to monitor not just the excavation for the tunnel, but also the surrounding buildings to ensure that they are not getting impacted because of the construction work that was happening in the vicinity. So what they had to do was to monitor various sensors. So they monitored uh, sensors that were monitoring basically piezometers that were monitoring the soil water pressure in the excavation area, and also strain and load sensors in the excavation area. And on these existing buildings, they placed tilt sensors to monitor whether these existing condominiums or residential buildings were tilting because of the neighboring construction work. So now, like they deploy the sensors, and they had to monitor the sensors like every hour while the excavation was happening to see again whether any unexpected movement or any unexpected happenings in the construction site. So with LoRa-based systems, they tried LoRa-based systems earlier. The problem was that the device or the sensors that were close by to the gateway could communicate the data directly to the gateway. But the other sensors that were far away from the construction site, far away from the gateway, could not reach the gateway directly. And right, if you recall what I mentioned earlier, in star networks, every device has to talk to the gateway directly. So if devices are too far away or if there are obstructions, that sensor data is practically unachievable. So in what the contractor did after that is they deployed our solution, which offered them a mesh-based system. So the result was that the devices, again, as if you recall, long-range mesh systems still have long-range communication links. So the devices that were even like a few hundred meters away could talk to the gateway directly, and the others that were too far, like some of these devices were in underground basements, like monitoring the car park. So those devices also could use long range links to talk to their neighbors and then relay that data back to the gateway. So when you have a mesh system as compared to a star network, you gain a lot more benefits, like there's more connectivity options, more connectivity paths available. So if paths get dropped or get obstructed, they automatically recover and send all that sensor data to the gateway. So this is how, at the end of the day, the contractor monitored that project. So now coming to part three. So in part two, essentially, just to summarize, what we discussed was the wireless technologies that are available in the industrial monitoring space, which fall into two categories: star networks and mesh networks. And we evaluated the pros and cons of both and argued why long-range mesh-based systems are better for critical infrastructure monitoring projects, because they offer many more benefits that like make monitoring very seamless or very easy to do in critical infrastructure monitoring projects. So now going into the wireless topic a bit further, I'll go into the solutions, like how a wireless solution works, and some case studies as well, to show you how wireless monitoring can really help gather geotechnical and structural sensor data in critical infrastructure projects. So I'll use our solution as an example to show you how these systems work in real life. So at Axio, we provide a wireless data acquisition system that can interface with existing geotechnical and structural sensors. So meaning, if you recall again, the sensors already exist in the market. And what we should do as solution providers is to help contractors monitor their existing piezometers, existing crack meters, existing tilt meters, and existing deformation sensors, like all existing sensors, using wireless technologies as opposed to using workers or cable-based systems. So that's what we discussed earlier. So what we provide is a wireless solution that essentially does that job. So how it works is that, again, as we discussed in the previous slides, so there are sensors that need to be monitored, like various geotechnical and structural sensors. So they are plugged into nodes, wireless nodes, and these nodes run on batteries. So you can place nodes right next to the sensors and connect the sensor to the node. and the nodes have wireless communication radios. So you can think of them like walkie-talkies. They can talk to one another using a patented long-range mesh communication protocol, and then they relay their data to the gateway. So the gateway is like the central device or which can collect all this sensor data, and then using an internet connection through a SIM card or even a Wi-Fi network, it can upload the sensor data to any software system or a central server where contractors and engineers can view that data to take real-time decisions. So again, as I said earlier, wireless solutions like the ones that we provide interface with existing sensors. So therefore, we have multiple kinds of nodes that support the different types of geotechnical and structural sensors that are used in the industry. So if you again evaluate the geotechnical and structural sensor space, there are three major kinds of sensors. So although they come from like hundreds of manufacturers, all these sensors are pretty standardized. There are three such standards called analog, vibrating wire, and digital. So if you're talking about analog sensors, there are things like tilt sensors or crack meters or like displacement sensors that fall into that bracket. When talking about vibrating wire brackets, there are sensors that monitor things like strain, load, pressure cells, and other sensors that are used in the industry. Now there are a lot of digital sensors in the market. So earlier, most sensors used to be either analog or vibrating wire, but in the industry, we see a lot of sensor manufacturers now producing digital output sensors that have like RS485, RS232, or STI12 outputs. So we have a node that supports those digital protocols as well. And apart from that, there's a tilt meter node which has an integrated tilt sensor inside the box. So when you install this like device on a wall, it actually monitors the tilt of the wall directly. Like you don't have to use any other tilt sensors. It's an like all-in-one tilt sensor with the tilt sensor and the wireless communications built into one node. There's a repeater node which acts as a repeater. Like let's say this tilt meter is too far from the gateway, so you can place a relay repeater node in the middle to act as a repeater. So it essentially takes the message from the tilt meter and passes it back to the gateway. And the gateway is, of course, as we discussed earlier, is the central device that collects all the sensor data and uploads to a central server. So I used our solution just to introduce like how these different components work in the monitoring solution, but you can find other solutions as well that use similar format. So now talking about how these wireless systems could be used for different types of projects, I'm using some illustrations for this purpose. So this is actually an illustration of a construction site to show how different geotechnical and structural sensors could be monitored wirelessly and remotely as well, using technology that we talked about earlier. So in construction projects, there can be sensors that monitor, like for example, tilt of these buildings, or if there's piling work, we can monitor the load on the different piling columns, and also if the total pressure of the soil can be monitored as well. And there can be there are sensors like deformation sensors, like in place inclinometers, for example, that goes into like multiple layers of the earth to monitor how different layers of the earth are deforming. And also if there's struts, the load on these struts can be monitored using load cells and strain gauges, for example. So all those different sensors can be connected to various nodes, as we discussed earlier. And the nodes would then use a long-range wireless mesh protocol, send the data to a gateway, and the gateway will then upload that data to, again, a software system or a central server that where you want to collect all that data. So with all that data, you can figure out whether this entire construction project is going smoothly, and if there are any unexpected movements in the soil or in the basement or in the piles or in the struts, then you can easily spot those abnormalities and take quick actions to prevent accidents and collapses. So same thing for dams. Again, if you're talking about a dam project, again, it's a very critical project carrying, and it can cost millions to build a dam. But if there are problems associated with the dam, again, the problems can be, the consequences can be devastating. So in mines, again, things like soil deformation, soil water pressure, tilt, and even some the water level of the water can be monitored using a wireless system like what we discussed earlier. So all those different sensors can be plugged into nodes and can be monitored using a wireless network through a gateway, which will help you to be informed of how the dam is performing. And if again there's something abnormal that is happening with the dam, uh, early actions can be taken to prevent any unfortunate accidents. So same thing for bridges. So if you're building a bridge or maintaining an existing bridge, again, several things can be monitored. Soil water pressure using piezometers, tilt on maybe the bridge, the columns of the bridge, strain and load on the different columns and members of the bridge. And also the strain and load that is being carried by the entire bridge can be monitored as well using various geotechnical and structural sensors. And again, those sensors can be monitored wirelessly and remotely using wireless technologies like what we talked about earlier. And finally, this is the last illustration to show how a rail project can be monitored. So there have been quite a number of projects in the rail sector that we've been involved in, where contractors monitor the tilt of the train track. So if there's some construction work or some movement in the soil near the railway track, it's important to monitor the track tilt, because if the track tilts, the trains that use this track might derail and cause lots of problems. So that's why track monitoring is important. Tilt monitoring of tracks is important. And if there are embankments or other areas that are close by to the track, they can be monitored as well using piezometers or deformation sensors or even tilt meters. So that's essentially 4 use cases that I quickly summarized, like construction sites, dams, bridges, and rail, to show how like critical these projects are, first of all, and how these projects can be managed by doing monitoring of geotechnical and structural sensors using wireless technologies. And to show you some case studies, this is the final part of the presentation actually. Just show some pictures to show how this is actually done in real life. So this is a huge excavation project where our solutions were used in the UK. And as you can see, these white like arms are actually props that were holding the excavation in place and ensuring that the entire thing doesn't collapse. So in this project, the contractors attached load cells and strain gauges to these props to monitor the load that each prop was carrying, to ensure that they were carrying the correct amount of load. Because if the load starts increasing, that means wall is giving way and everything can collapse. So the project was completed very recently and it was quite successfully done because they carried out real-time monitoring of the strain gauges and load cells using our technologies. This is a project that is still ongoing in Peru. So the mountains that you see are the Andes mountains in Peru. And this particular mountain that our client was monitoring is quite susceptible to landslides. So the authorities wanted to monitor whether this mountain is, the slope of the mountain is stable, and whether there would be any landslides that can be pre-detected so that they can take in and go and reinforce the slope in case the sensors pick up any movements in the soil. So in this project, they deployed about 30 wireless tilt meters across the slope and monitored them using a single gateway that was powered with a solar panel. So the tilt meters was all spread across the entire slope of the mountain, and then they placed a gateway powered with a solar panel in a central area. So all the tilt meters were sending the data wirelessly to the gateway here, and from the gateway, the data was uploaded to the contractor's software system, where they monitor the sensors on an hourly basis. This project, this is complete. This is actually in Hong Kong, where the authorities built a dual tunnel expressway that went under the sea. So it's a very critical project because again, there's a lot of excavation. It's going under the seabed. So there's a lot of movement or movements in the structures or in soil that needed to be monitored. So the automated monitoring of soil, like for water pressure sensors like piezometers, tilt meters, strain gauges, and load cells that were monitoring the load on all these different members, column members, and the walls of the tunnel using our wireless communication systems. This project is in Singapore. So if you've been to Singapore, Changi Airport is Singapore's one and only airport. So they are building a new train tunnel to connect a few of the terminals, so that passengers can take just one train system to transfer between different terminals. So as you can see, there's a lot of excavation that is happening to build that new tunnel. There are multiple layers of struts as well that have been used in that project. So all those struts were like had strain gauges and load cells attached to them, and those strain gauges and load cells like were mounted using our wireless devices. So the black wires that you see, they terminate at different sensors, and that sensor data comes to our node through which the data is then transmitted wirelessly to a gateway that was placed at the site office, and the gateway then uploads the sensor data to the contractor software system. And the one on the right is an existing train track that is currently being used in Singapore, but because that's very close by to an adjacent construction site, the contractors placed tilt meters on the track bed to monitor whether the track is tilting over time. And the last one, the last case study that I just wanted to show you is again another project from the UK, where tilt sensors were used, tilt sensors and deformation sensors. So this sensor that you see here, this pipe actually, the borehole goes about 100 meters into the soil. So they were monitoring the deformation of the various soil layers near the track, as well as the tilt of this embankment, to ensure that any movements that happen do not obstruct the train track. So this entire area was again susceptible to a lot of movements in the soil. So that's why the authorities wanted to monitor the tilt and the deformation of the soil or the embankment to ensure that the train operations proceeded smoothly. So that's actually pretty much it for today's presentation. I just wanted to go through a few points to show how geotechnical and structural monitoring can be done using wireless technologies to achieve higher productivity, higher safety, and achieve cost savings as well. So just to summarize today's talk. So first of all, we discussed why infrastructure projects need to be monitored using geotechnical and structural sensors, because such monitoring processes help contractors reduce costs, increase productivity, increase the safety, and also in some countries achieve regulatory compliance as well, like in Singapore, as we discussed. This entire monitoring process of geotechnical and structural sensors is regulated. So in order to meet these regulatory requirements, you have to monitor them, and doing it wirelessly can help them meet those regulatory criteria in an efficient way. So we also discussed how they are being, how geotechnical and structural sensors are currently being monitored. Yeah, like all the legacy solutions that are used, like for example, using manpower and cables, and we discussed the limitations that are associated with them as well. And then we discussed why wireless monitoring is better, a better suited alternative for monitoring geotechnical and structural sensors. And we then looked at how different wireless technologies work. And we also discussed why long-range mesh-based systems are better suited for monitoring critical infrastructure projects, because they have higher reliability. The key thing that they offer is higher reliability, which offers all the sensor data. Like if there are about, say, 1,000 sensors that need to be monitored, mesh networks, long-range mesh networks can offer very high reliability in monitoring all those 1,000 sensors. And therefore, the contractors and stakeholders get all the data that they require to take real-time decisions. And finally, I introduced some of the solutions that we provide and went through some case studies as well, where the solutions have been used to implement advanced monitoring solutions in the critical projects that we've been a part of in construction, mining, rail industries. So that's pretty much it in terms of the presentation. So if there are any questions that you have, I'd be happy to answer them now.
Okay, thank you, Dr. Nimant. So any question you can, put it into the chat box so that we can answer it.
So there's a question from Ismail Irfi, and the question is, what kind of technical skills are needed for instrumentation? So there are two kinds of skill sets, I would say. So one is the geotechnical and structural monitoring skill set. So this is an area where, as a company, we don't get into. So this entire monitoring area is carried out by specialist geotechnical and structural monitoring contractors. So these contractors work with consultants to figure out which things need to be monitored, which areas of the project require monitoring, and how frequently do these sensors need to be monitored. So typically that part is being done by geotechnical instrumentation companies. So once they have laid out the monitoring plan and they know what sensors to install and where to install, that's where we get involved. And we would look at the instrumentation layout map and say, okay, you have like 1,000 sensors that are scattered around in this tunnel, and these, like, the first 10 sensors can be monitored using one node. The second set of sensors can be monitored using the second node, and so on and so forth. So we help them come up with a wireless network to monitor those sensors using our technologies. So the first part of instrumentation and monitoring, that is a civil engineering skill set, and that has been done by geotechnical engineers typically. The second area where deploying a wireless network, that is where we help geotechnical monitoring contractors like with. So it's essentially help them plan out a wireless network that can help them monitor those sensors. So I hope that I answered that question.
Yeah, Engineer Samudya Nanakara wants to. He's raising in it. Yes, Engineer Samudya Nanak. There was another question, Dr. Nimant, the chat box.
Okay, sure. So the second question is from Engineer Khandiban. So in the mesh network, how long is the battery life of sensor node? So this is a good question, and it totally depends on the type of sensors and how frequently they are monitored. So for most sensors, I would say the devices last anywhere between 3 to 5 years. But if you're monitoring very frequently, like let's say every 5 minutes, then the battery life can be like 1 year. And also type of sensors also matters, because like simple things like a tilt meter doesn't consume a lot of power. So if you're monitoring a tilt meter, like let's say once every 6 hours or once every hour, batteries can last anywhere close to 3 years. But let's say you're monitoring a 100-meter long in-place inclinometer that goes deep into the tunnel. So there are like multiple sensors in the sensor chain that goes like 100 meters into the earth. So such sensors consume more power, and in which case the lifetime would be quite lower. So yeah, it totally depends, Kandiban. So if you have like a project where like, where we can look at the kind of sensors that are you're planning to use, we can definitely take a look at it and advise on what the actual lifetime would be. So there's another question from I think Engineer Abdul. How long will it take the monitoring system for stability? Not sure exactly what you mean here, because the monitoring system is typically deployed to monitor existing sensors. So again, if you're talking about the stability of the infrastructure project, like the tunnel or whatever is being monitored, in that part is typically handled by geotechnical monitoring engineers, as we discussed earlier. So any sensor that is required to monitor the stability will be determined by those engineers, and we then help them monitor those sensors using wireless technologies. If you're talking about how, in terms of stability, like how stable the network is, mesh networks are pretty stable as compared to star technologies, as we discussed earlier, because if there are obstructions or interference, the mesh systems automatically figure out alternate paths instantaneously, and therefore they can circumvent any problems or obstructions that might occur in the site. Moving forward, there's a question from Engineer Surya Bandara. How about accuracy of wireless systems and cost comparisons? So the wireless systems, the key thing to note is that they don't affect the accuracy because wireless systems typically monitor existing sensors. So if you are using a very accurate hill sensor, the wireless system would read that data and collect it with the same accuracy that the sensor is providing, and now transmit it wirelessly, as opposed to reading it manually or with a cable. So wireless systems typically do not offer higher or lower accuracy, because the accuracy property is actually a property of the sensor. But what wireless systems do is they make the process of monitoring that sensor more reliable. Because if you're using a cable might get cut and you might not get data for like few days. If you're using a worker, again, they might not read the sensor very accurately. So it's very difficult to depend on manual readings. But if you're using a wireless system, they will collect the sensor data with the correct accuracy, or with the same accuracy that the sensor is able to provide, and then convey that data reliably back to a central server or a surface system. Yeah, there's another question from Dr. Samuday, I think. So how is the security of the network? So this the security is actually many systems in the market use different kinds of encryption technologies. So the most commonly used one is AES-128, and that's what we use in our system as well. So AES-128 provides like it's a symmetric key security system, of course. So like different keys can be used in different deployments, so that different networks don't start interfering with one another, and offer like very high security as well. Public key infrastructure systems have not been deployed a lot in this space. There are a few companies that we know who are looking at how IoT devices can leverage public key infrastructure based security systems. But again, there are quite a number of practical difficulties in deploying them out into these kind of low power wireless systems. So they haven't really garnered a lot of adoption. So symmetric key systems like AES-128 are more popular, and that's what we use as well. There's another question: how much of a budget would be needed to set up a LoRa or ZigBee network? So I guess this question is with regards to the costs. So it totally depends. I mean, there are solutions. ZigBee is typically not recommended for infrastructure monitoring projects, like because again of the range limitations. ZigBee uses very less power, so you can even power them using coin cell batteries, like the batteries that we use in our watches. But the problem is the range is quite low, so they have a very severe range reductions in when you deploy them in a construction site or a tunnel or a mine. So LoRa is the other alternative that you can definitely look at. But as we discussed with LoRa, again, for simpler projects, it might be quite okay. And there are lots of like LoRa-based solutions in the industry already. But when it comes to tunnels and underground environments, that's where, or bigger sites, that's where LoRa solutions have limitations. So in terms of budget, it's very difficult to say. ZigBee is not used a lot. LoRa devices range from anywhere between a few $100 to thousands of dollars. Like you can find solutions anywhere between those price ranges. And then there are like do-it-yourself LoRa systems as well, because it's very simple to build. You can buy off-the-shelf LoRa chips and try to connect them with existing sensors to build a LoRa-based communication system. If have any systems use satellite data? So yes, there are INSA-based systems. Again, this is a space that I don't personally have a lot of knowledge in, but there are companies that are using satellite-based systems like INSA systems to do displacement monitoring. So the traditional way that contractors do deformation monitoring or settlement monitoring is they use total stations or surveying equipment, where they go around with like total stations or the light-based systems to monitor how different points in the earth or in the structure are settling. But now there are companies that are offering satellite-based solutions that can do this without any human intervention. So they use a different kind of satellite technology called radar satellites, where they send a radar signal from satellite to the ground. And then by using the time of flight property, they can evaluate to sub-millimeter level how the ground is deforming. So it's a very fascinating technology. It's pretty new. I have read some case studies of projects where satellites have been successfully used to monitor settlement in the UK and France. I think in Australia as well. But yeah, again, like in Singapore, there have been several POC projects where INSA technologies have been used to monitor settlement. But again, it's an area that I don't have a lot of knowledge in. So sorry, I can't share more than that. Does this monitoring system warn us based on upper lower bound critical values? Or yes, definitely. So this is one of the key features of any real-time monitoring system, and it is the case with wireless systems as well. So for each sensor, you can set thresholds on the readings, and when the readings cross any of these thresholds, you can configure them to raise alerts, like email alerts, for example, can be sent out if if a sensor breaks those thresholds. So this is actually a must in Singapore, because as I mentioned, most monitoring projects are regulated. So for every sensor, the consultants and the authorities would set limits. Like for example, if they're monitoring a tilt sensor, they would say that the tilt cannot be more than like 0.002 degrees. So that 0.002 degrees then it then gets fed into the system as a threshold. And then if while monitoring the sensor, if any of the readings cross that threshold, like 0.002 degrees, the system automatically sends out an alert, so that the engineers can take, like, first of all, investigate why the threshold was breached, and then they can take actions to ensure that the tilt doesn't go beyond that, or even like fix, if the column is tilting, they can take actions to fix the problem. Yes, so then another question. Yeah, so I think he's asking whether unmute or yeah, this engineer. I think yeah, it's fine. You can ask the question by unmuting, or you can type it in as well. Engineer Mustari, I think there's a request to allow participants to unmute.
Yeah, we
have.
we are arranging that.
Okay.
give us few seconds, 1 minute. They will, the co-host will do the needful.
Okay. Yeah.
No,
Thank you
it's
very
okay,
much.
right? Yeah.
Yeah, it's working now. Yeah. Thank you very much. Thank you very much, Nimand, for your nice presentation. I think let me introduce myself. I am Dr. Navaratna Raja, senior lecturer at the engineering faculty, Peradeniya. I also, teach this instrumentation and monitoring for our postgraduate students here, and I also worked in FEEV instrumentation project in USA sometimes back. I think this is one of the area very rarely practiced in Sri Lanka.
Yes.
I think it is now time that we introduce these type of things to Sri Lankan practicing engineers, because this will bring a lot of benefits to, especially for the big projects. I have one question. You mentioned about there is a cost effective when we go for a wireless technology. I'm sure that it depends on the number of instruments that you monitor in a project. Say, for example, if you are monitoring like a FEEV number of instruments, I mean, maybe a manual system may be cost effective. But if you go for like a many number of and different complicated instruments, I think the wireless will give a lot of benefits and save a lot of money. But again, like even if there is a fee things to be monitored in some of the project, you can't avoid going for a kind of a remote monitoring, such as like what you said on a slope monitoring, where the slope is dangerous. Manual reading is most of the time is not possible because of the danger involved. My question is like how you decide as a company, you provide a wireless system, how you recommend to your client, when to go for a kind of a remote monitoring system. Like, I mean, do you have any kind of a criteria based on like, what I mentioned before, like how you recommend your project clients on this going for a wireless technology?
Yeah, that's a great question, Dr. Navaratna Raja. Thanks for raising that. Let me quickly show you a table that we did where we actually discussed that scenario. Just give me a second. Let me find it and share it with you.
Thank you.
Yes. Okay. Let me share my screen again. Yes. So
please keep your mic muted on. Okay, thank you.
So this is a table where we, and your comment is absolutely correct, Dr. Navaratna. It's not every project is suited for automated monitoring, first of all, and even when deciding between cables and wireless, still there might be scenarios where cable might be a better alternative as well. So yeah, so this table summarizes those three scenarios. Like for example, if the monitoring interval is low, like we have seen some projects in Singapore, where initially they start off with manual monitoring and then they transition to automated monitoring, like wireless monitoring. So it's because, like, let's say there's an excavation that is happening using a tunnel boring machine or a TBM for an underground tunnel. So while the TBM is very far away from, let's say, a certain residential area, that area is not monitored very frequently, like maybe once a week or once every 2 weeks. Like if there are tilt sensors, they'll monitor just maybe once every 2 weeks. So if the monitoring interval is very low like that, manual monitoring works because you can afford to send a worker once every week or once every 2 weeks to monitor them. But let's say the monitoring interval is very high. that's when you need to consider going into an automated system, either using cable or wireless. The second is I've not mentioned here, but the second property is how essentially the spacing between the sensors. So let's say the sensors are scattered or scattered around the construction site, and they are very far from one another. So in which case, it's better to do a wireless monitoring system, because you don't have to then draw very long cables to connect all these sensors. With wireless systems, you can place the transmitter close to the sensor, and that helps transmit the data reliably. But if the sensors are if there's a cluster of sensors, like you just have a few sensors, as you mentioned, in close by, it might make sense to cable connect all of them to a central data logger, and then you might be able to monitor them easily. So you're right in that comment. Like, not every project is suited for wireless monitoring. Some projects you might be able to do manual monitoring if the monitoring frequency is not very stringent. And also, if the sensors are not very far off, you might be able to do cable-based monitoring. But yeah, if the monitoring frequency is very high and you have lots of sensors scattered around in the entire construction site, in that case, wireless monitoring would be a better solution.
Yeah, thank you very much. Actually, while you are explaining, I just got the screen capture of this particular slide. Hopefully, you give permission to use this slide in my lecture slide.
Please go ahead.
Thank you very much. Yeah, it's nicely put together what exactly I asked for. Thank you very much, and thank you very much for your presentation.
No problem, Dr. Narada. Yeah, my pleasure.
Thank you.
Okay. So, Dr. Samudya, you want to ask any question? You raised the hand. Right. Please unmute your mic, please. Please unmute your mic, please. Right. Okay, Engineer Samudya, you can go ahead.
No, Engineer Mr. I already asked the question, and Nimant answered that one. It's about the communication security thing. Yeah. Thank you very much, Nimant. That nice presentation. It's really informative.
Yeah. So
Thank
yeah,
you.
it's a great presentation. Achini, over to you. Engineer Achini, over to you.
Thank you, Engineer Mustali. Good evening, everyone. I'm glad to be present here to express my vote of thanks. Firstly, on behalf of IT and Computer Engineering Sectional Committee, we wish to express our sincere gratitude to IESL President, Secretary, and staff. And special thanks to Dr. Nimanta Baranasuriya, who has given his precious time to conduct this event from Singapore. And we are thankful to him for sharing his immense knowledge on industrial IoT with the engineering community. Once again, many thanks to enable this evening to have a successful event. Also, I'll take this opportunity to thank our organizing team of IT and Computer Engineering Sectional Committee for helping us to arrange this public lecture. We are organizing this kind of events to uplift IESL in all aspects. Finally, I extend my big thanks to all the participants who make this event successful. Thank you, everyone. Have a pleasant day and stay safe.
Thank you. Thank you so much, Dr. Nimanta. Thank you.
Yeah, thank you very much, Engineer Mustali and Engineer Ashmi, for inviting me as well. It was a pleasure to be here to discuss this topic. So yeah, thank you very much once again for having me, and thank you very much to all the members who participated today as well. Yeah, it's a lovely occasion.